Yeah.
Okay, it's recording.
We are very happy to have Cristian Lenart from Albany. Cristian will talk about from Macdonald polynomials to Schubert calculus in quantum K-theory.
Thank you very much for the invitation. Thanks everyone for coming. So I will talk about this excursion from Macdonald polynomials to Schubert calculus. This is some part of it is a survey of previous results of various people, and it also contains joint work with my Japanese collaborators, Satoshi Naito and Daisuke Sagaki, which is mostly contained in the first paper here, indicated, and also some papers with Takafumi Uno. So please feel free to interrupt me at any time to ask questions. So, right. Okay, so I'll start with the classical story, which is the basis for my talk. So there is a close connection between representation theory of semisimple algebras and geometry of flag manifolds G mod B. So G is complex semisimple Lie group and B a Borel subgroup. And then there is related combinatorics. So there are combinatorial models which apply to both areas because of this close connection. So this is very classical, and I'll say a little bit more about it. But what we want to do here is to seek quantum/affine version of the story. Actually, there is something called the quantum equals affine phenomenon, which I will mention later. So what does this exactly mean? So it means that we want to replace representations of semisimple algebras with representations of the corresponding quantum affine algebras. Then we want to replace flag manifolds G mod B with their affine versions. So I will make this more precise. Then I will also replace K-theory with a quantum version called quantum K-theory due to Yuan-Pin Li, and which attracts now considerable interest. And in the story, the Macdonald polynomials are involved, and they will arise as Q characters. So let me start with some notation. So G is, as I said, a semisimple Lie group over C, so the traditional root system notation. T contained in B contained in G are the maximal torus and the Borel subgroup. Then N, the unipotent radical. P is the weight lattice. Omega I, the fundamental weights indexed by nodes of the Lincoln diagram. P plus the dominant weights. Q, the root lattice. Q check, the core-root lattice. Alpha I, the simple roots. And then we have the group algebra of the weight lattice identified with the representation ring of the torus. So this is algebra spanned by formal exponentials, e to the lambda, lambda being the weight. And then we have the finite Val group generated by SI, the simple reflections, and W0, the longest element. So all traditional notation. So now with this notation, I can explain the classical story I mentioned at the beginning. So we need to consider T-equivariant K-theory of the flag variety G mod B as a module over the K-theory of a point, which is identified with the representation representation ring of the torus or the group algebra of the weight lattice. And this has a basis of Schubert classes denoted like this. And these are classes of structure sheaves of Schubert varieties defined as the closures of these closures BW, B mod B. So they're indexed by elements of the finite Val group. So for each weight, there is a line bundle on the flag variety denoted L lambda, defined like this. So we consider a character of the torus, and this defines a one-dimensional representation of the torus, extend it to B, and then take the the product with G. So then the Chevalley formula is the simplest multiplication formula you can write down in equivariant K theory or maybe cohomology. So it expresses the product of Schubert class, arbitrary Schubert class, with the class of this line bundle. So when you expand in the basis of Schubert classes, you get these equivariant coefficients e to the mu, and then some integer coefficients. So we want to write this explicitly. And then the connection to representation theory comes by considering de Mazur modules. So these are certain B modules for the corresponding Lie algebra or Lie group. So they are these modules V sub W of lambda. So they are submodules of the highest weight representation with highest weight lambda for lambda dominant weight, and W an element of the finite vowel group. And then the connection to geometry is made by this Borel-Weil theorem, which implies that the character of the de Mazur module is obtained simply by is obtained from the Chevalley formula simply by ignoring the Schubert classes here. So you just sum up these integer coefficients times e to the mu. So this records the dimensions of the weight spaces in the de Mazur module. And then there are combinatorial models which allow you to write this Chevalley formula explicitly to determine these integer coefficients here, and also therefore to write the de Mazur character. And these are various models. For instance, Lakshmi by Seshadri paths is a classical model. Then more generally, we have Littleman paths. And then we have a discrete version of these path models that I developed with Posnikov, called the alcove model, and which I developed even more since then in various directions. And I will mention the alcove model soon. So then I said that the Macdonald polynomials come up in the story. So they are polynomials associated with an irreducible affine root system with rational function coefficients in Q and T. And they are connected to many different areas, for instance, representations of affine Lie algebras, p-adic groups, integrable systems, statistical mechanics, and so on. And there are two versions. There are the symmetric ones. The symmetry is here with respect to the vowel group action, finite vowel group action. So these are indexed by dominant weights lambda. And as I said, there are polynomials in X with the coefficients, rational functions in Q and T. And when you specialize Q equal T equals 0, you just recover the irreducible character corresponding to the highest weight lambda. So there are certain deformations of this character, one way to view them. And then there are non-symmetric versions, E mu. Mu here is an arbitrary weight now. These are defined and constructed recursively in the setup of the double affine Hecke algebra, but I don't have time to say more about that. And then the symmetric ones are obtained by a certain symmetrization of the non-symmetric. The non-symmetric ones, when you specialize similarly Q equal T equals 0, you recover the de Mazur character. So here's my first slide of a Q version, of a quantum affine version of the connection between representation theory and geometry. So this was the state of the art around 2011, 2014. So let me explain this a little bit. And I won't go into much detail because then I want a more complete version of the story. So on the representation theory side, we have these Kirillov-Reshetikin modules. Actually, if I remember well, I talked about them and the quantum alcove model around 2016. I think I visited CUNY again, and I gave a talk in the seminar about about this connection to Macdonald polynomials and the quantum alcove model. So this is work of myself with Naito-Sagaki, Schilling, and Shimazone. So there are these modules for the affine algebras, and they are not the integrable highest weight modules, because those are infinite. These are certain finite modules for the affine algebras, and we connected them to certain specializations, actually at t equals 0 of Macdonald polynomials, of the symmetric Macdonald polynomials. And then we showed that an extension of the alcove model called the quantum alcove model gives you formulas for the characters of these and for these specialized Macdonald polynomials. And going towards geometry, Braverman and Finkelberg related these specialized Macdonald polynomials to something they called q-Whittaker functions. And then further, they related the q-Whittaker functions to quantum K-theory of the corresponding flag variety. And here there is a dotted arrow to the quantum alcove model because, first of all, we had a conjecture of myself with Postnikov and Maeno that the quantum alcove model also gives the Chevalley formula in quantum K-theory. And this was not proved at the time. It is proved now, and I will talk about that. But there is another reason why this arrow is dotted, because this connection coming from above and coming from below does not quite match up. And let me explain this a little bit. So first of all, just very briefly, the q-Whittaker functions are defined as, by Ettinghoff and Sebastianov separately, are defined as eigenfunctions of the so-called quantum difference Toda integrable system. And this also governs the structure of quantum K-theory, as shown in type A by Giventhal-Lee and in general by Braverman-Finkelberg. So in simply laced types, the connections I mentioned before, what they are more explicitly, they say that the q-Whittaker functions are equated with the Macdonald polynomial symmetric one specialized at t equals 0. And in quantum K-theory, they are equated with the so-called K-theoretic J function. And this is the generating function of the so-called one-point K-theoretic Gromov-Witten invariants. Now, these Gromov-Witten invariants, they give you the structure constants, the multiplication of Schubert classes in quantum K-theory. This is how the multiplication formula is defined in quantum K-theory, and it's a remarkable fact that you get an associative algebra in this way. But it's not an easy definition. Basically, you have to take the so-called 2- and 3-point K-theoretic Gromov-Witten invariants and then plug them into a complex formula, and that gives you the structure constants in quantum K-theory. So what's important to notice here is that this K-theoretic J function involves the 1-point invariants, and the structure constants in quantum K-theory involve the 2- and the 3-point invariants. So that's why I said that these connections here do not quite match up, because on the top, the connection to quantum K-theory from Braverman-Finkelberg involve these 1-point invariants, whereas our conjectured multiplication formula, Chevalley formula, because it's a multiplication formula, involves the 2-point and the 3-point invariants. So here it doesn't quite match up at the top. The 1-point invariants are weaker in a sense. In principle, you can use them to get the 2- and the 3-point invariants, but that's very complicated. So I won't talk too much about that because I want to get to a more complete picture. But before I do that, I want to explain the underlying combinatorial model, because all of this representation theory and geometry has underlying combinatorial models. And that's the quantum alcove model for me. So this combinatorial model is based on very elementary structure called the quantum Bruja graph. So this is a graph on the finite vowel group, which you basically get from the Bruja order by adding extra edges. So again, W is the finite vowel group, and the graph has labeled edges from some element W to WS alpha. S alpha is some arbitrary reflection corresponding to, let's say, a positive root alpha. And you have such an edge whenever the length increases by 1 upon this right multiplication. So these are the covers of the Bruja order. Or the length decreases by a large amount. So this is twice the height of the core root minus 1. And the height you just get by expressing the core roots in terms of the simple core roots and summing up the coefficients. So this might seem strange, but actually it's very natural. First of all, it arose in the first time in the Chevalley formula for quantum cohomology of flag manifolds, Fulton and Woodward. And then it's become more natural since it has a lift to the covers of the Bruja order on the affine vowel group. So this was explained in detail by Lamm-Schnozono. So as an example for S3, so in type A2, you have the 6 permutations of 1, 2, 3 with the identity at the top and the longest element. Identity at the bottom and the longest element at the top. And these are the covers of the Bruja order labeled by the corresponding roots. And then you have to add these down edges, the quantum edges. For instance, from 3 to 1, if you switch 1 and 3, you get the identity, and that's a large drop in length. But notice that not every arrow has an inverse red arrow. The arrows for the simple roots, they always do. But then there are other down arrows. So then I can describe the quantum alcove model. Its main feature is that it's a uniform model for all root systems. It's built in the setup of a finite root system, but then it applies to Macdonald polynomials, which are in the setup of affine root systems. So we start with a weight lambda because we want to write these characters or Macdonald polynomials are indexed by lambda. So we fix a weight lambda. And this is arbitrary now. And with it, we associate a sequence of roots called the lambda chain. So just a sequence of roots which can be positive or negative. How is this determined? This is determined by a reduced decomposition of the affine vowel group element, which sends the fundamental alcove to its translation by negative lambda. So this reduced decomposition determines a sequence of adjacent alcoves, shortest sequence, joining the fundamental one to the translated one in the usual way. So for instance, here is in type A2, if you take this weight 310 partition, so 3 epsilon 1 plus epsilon 2, which now it's dominant, but in general, it can be any weight. Then you look at, so here is the origin, here is negative lambda. So you have the top shaded alcove is the fundamental alcove. In red, you see the positive roots. And the coordinate vectors, their projections are epsilon 1, epsilon 2, epsilon 3. So then we take this blue path, which joins the fundamental alcove to the translated one. And the lambda chain is obtained simply by recording all the walls that are crossed, all the hyperplanes that are crossed in order. So the first crossed hyperplane is orthogonal to the root 1, 2, epsilon 1 minus epsilon 2. So that's the first root in the alcove path, and then the second hyperplane crossed is orthogonal to 1, 3, and so on. You have all in all 6 roots because there are 6 hyperplanes crossed. And we will also need these affine reflections corresponding to these affine hyperplanes, and I denote them with R hat. So the lambda chain is just a collection of these non-affine roots corresponding to the hyperplanes. Ri is the non-affine reflection corresponding to the root beta I, and Ri hat is the affine reflection corresponding to the ith hyperplane in this sequence of crossed hyperplanes. So the objects of the model are now subsets of positions in this chain of roots. So just some indices J1 through JS, subset of 1 through M. So you have 2 to the M such subsets. But there is a condition for selecting these subsets. So to explain this condition, you have to associate with this subset of indices a chain of elements in the vowel group. You fix some element W, which is the starting element, and then you multiply one by one on the right by the reflections corresponding to these positions, J1, J2, JS. So W, WRJ1, WRJ1, RJ2, and so on. And you end with some element where you multiply with all the J1, JS. This we call end of WNA. And then the condition is that this chain, the sequence of vowel group elements, to give you a path in the quantum Bruch graph. And here the up edges can alternate with the down edges in any order. So just a path. So we call this this family of subsets. We call it A of W and gamma. Gamma is the lambda chain. W is this starting element, and these subsets in this collection are called the W admissible subsets. And then we need to write formulas. We need to associate some statistics with a pair WA, where A is such a W admissible subset. N of A is just the number of negative roots. If you just look at the roots in the lambda chain, only for the positions J1, JS, and you count the negative roots there, that's N of A. Then there is a weight. You just consider the affine reflections for the positions J1, JS, apply to negative lambda, then apply a W and change the sign at the end. A minus is the subset of this set of indices where you have down steps in the corresponding chain of elements in the vowel group. Remember, we associated this chain of elements by multiplying on the right. So whenever you multiply by the ith reflection in this subset of positions, you get a down step in the Bruch order, and in the quantum Bruch graph, then you record this position as part of this negative part of the set A. And then down of WA is just a sum over these negative positions where you have down steps of the corresponding root in the lambda chain. Actually, you take the core root, and these bars just indicate that if it's a negative root, you change it to a positive root. So this sum lies in the positive part of the core root lattice. And then the height is just a number. The height of the pair WA, again, you sum over the positions where you have down steps, and you sum these levels, but they are complemented. They are some sort of complementary level of the corresponding hyperplanes, in the sense that you take the usual level and you subtract it from the maximum level, which is lambda beta I check. And then there is also a notion of co-height, where instead of these complementary levels, you just sum the usual levels. The levels are, again, just given by these affine hyperplanes in position I, this negative Li. And when lots of times this fixed element W is just the identity, so then we just omit it and we say A of gamma, weight of A, co-height of A, so we just drop the W from the notation. So then with this notation, I can express some combinatorial formulas for the non-symmetric Macdonald polynomial specialized with T being either 0 or infinity. And I can express that in terms of the quantum alcove model. So here we fix a dominant weight, and we fix a lowest coset representative modulo the stabilizer of the weight lambda. So this I call W upper lambda, the lowest coset representatives. And I use this notation floor for an element V to simply mean that in the coset of V modulo this the stabilizer, I take the lowest coset representative. So I just map an element to the lowest coset, to the lowest representative of its coset. So then one formula we gave with Naito-Sagaki, Schilling, and Shimazono, based on the Ramyib formula for Macdonald polynomials, by specializing it, and the specialization, I did it, and then Shimazono also gave several such specializations. This says that the non-symmetric Macdonald polynomial indexed by W applied to lambda, so lambda is a dominant weight, and you apply W so it becomes an arbitrary weight. When you specialize T equals 0, it just becomes a positive sum over the sets in the quantum alcove model, these admissible sets. But you only need to select those for which the end element is, well, rounded down, is less or equal to W. And then you have the statistic Q to the co-height, X to the weight. So it's a nice explicit positive formula for the specialized Macdonald. And then there is a similar formula given by Shimazono, again by specializing the Ramyib formula for Macdonald polynomials, which works for the specialization T equals infinity. So finally, I can now explain the more complete version of this connection from representation theory to geometry to combinatorics. So here again, I start with specialized Macdonald polynomials at T equals 0 or T equals infinity. So these were related by my work with Naito-Sagaki, Schilling, and Shimazono, and then other work by Naito-Sagaki and collaborators of them, to these so-called level 0 extremal weight modules for affine algebras. And then Kato-Naito-Sagaki related these affine modules to the K-theory of T-equivariant K-theory of a certain affine flag manifold, but not the standard one, a certain non-standard version called the semi-infinite flag manifold. And then Kato recently had a breakthrough which related this K-theory of the semi-infinite affine flag manifold to quantum K-theory of the finite type flag manifold. And then the quantum alcove model gives you formulas. It's a model for all of these algebraic and geometric structures. And the most recent result is mine with Naito and Sagaki, which used the quantum alcove model to give a Chevalley formula in quantum K theory, which was our conjecture with Postnikov and Maeno. So I will spend the rest of the talk explaining this diagram, all the concepts here and the connections between them. So I'll start with the representation theory. So you take an affine Lie algebra, GF, and the corresponding quantum affine algebras, deformation of the enveloping algebra, UQ of GF. And if lambda is an affine weight, then you have the so-called extremal weight module of extremal weight lambda over the quantum affine algebra. This is denoted V lambda, and this is generated by a vector of weight lambda, V lambda. And when the weight lambda is of positive or negative level, then V of lambda is the usual integrable highest or lowest weight module. Now we focus on level 0, where the structure is more complicated. And this is level 0 is connected to Macdonald polynomials and to the geometry. And then if lambda is a finite dominant weight, then there is a de Mazur submodule of these level 0 extremal weight modules, which is just obtained in the usual way. So there is a de Mazur module and an opposite de Mazur module indexed with plus or minus, corresponding to some affine Wald group element X, which is obtained in the usual way by taking the upper or the lower triangular part of the affine algebra and acting on the corresponding weight vector, extremal weight vector, X applied to V lambda. So this is a submodule of the level 0 extremal weight module. So these are highly infinite modules. These de Mazur modules are highly infinite, but there are some nice finite dimensional quotients. So Beck and Nakajima, for the usual de Mazur module, they defined a quotient called the UVW, the UW plus of lambda, which is finite dimensional. And then there is a graded character, which you obtain in the usual way by recording the dimensions of the various weight spaces. And you introduce a variable q, and the q is just x to the delta. So it's a q character. It's a graded character. So then you have connection between representation theory and specialized Macdonald polynomials. So the first one, which relates to these quotient level 0 de Mazur modules. So the first one says that the graded character of this quotient by Beck-Nakajima of the de Mazur module is its graded character is just the specialized Macdonald, non-symmetric Macdonald polynomial specialized at t equals 0. And then we can say more about the structure of this module. We can look at the so-called Kashwara crystal of this quotient module. The crystal is just a combinatorial shadow of the representation. So the crystal is a directed graph whose vertices index the basis elements of the representation, and the arrows record the action of the Chevalley generators in the limit q goes to 0, q being the q from the quantum algebra. So this crystal, this color-directed graph, is described in terms of the quantum alcove model. So the vertices of the graph are just the admissible subsets in the quantum alcove model for which this end element is less or equal to W in Bruch order. And then one can also describe the arrows in terms of these admissible subsets. And so all this happens for the quotient modules, for the finite dimensional ones, but one can also look at the actual level 0 extremal weight modules, de Mazur modules, and the corresponding crystal, which is now an infinite graph. This can be described in terms of so-called semi-infinite Lakshmi-Seshadri paths. So these are, again, some piecewise linear paths where the directions of the paths are now indexed by elements of the affine Wald group. So this is a result of Naito-Sagaki. And then we have analogous results to all of these for the opposite Damasur modules, for the ones indexed by minus. So here, there are also some finite dimensional quotients called van der Kallen modules defined by Naito-Sagaki. And the relevant specialization of Macdonald polynomials is the one for t equals infinity. So for the opposite Damasur modules, you need t equals infinity. And all of these results have analogs. So finally, let me go to the geometry. So here we need a non-standard affine version of the flag manifold, G mod B, called the semi-infinite flag manifold, which was defined by various people listed here. So this the semi-infinite flag manifold is denoted QG-rat. So it's associated to a complex semi-simple Lie group G. And formally, it's a reduced in scheme associated to this quotient. So you take the Lie group over former Laurent series in Z, and then you quotient out by T times N over Laurent series. And here we have Schubert varieties as well, denoted by QG of X. So the Schubert varieties are indexed by elements of the affine Val group, which you look at as the semi-direct product of the finite Val group with the chord lattice. And we concentrate on the Schubert cell corresponding to the identity. And here there is a T cross C star action. There is a torus action and also a C star action coming from loop rotation. So QG will be what I will call semi-infinite flag manifold. So it's technically just the Schubert cell corresponding to the identity. This is like the most important part of the semi-infinite flag manifold. And one takes equivariant K-theory with respect to this T cross C star action. So the equivariant K-theory of a point is the group algebra of the weight lattice with coefficients Q and Q inverse. So the Q corresponds to the C star action. And here we have a basis of Schubert classes denoted as usual. And these are now indexed by only the positive part of the affine Val group. So the semi-direct product of the finite one with the positive part of the chord lattice. So just positive sums of simple chords. And then for a weight lambda, we have weight lambda, finite weight lambda, we have a line bundle similarly on the semi-infinite flag manifold and also on a Schubert variety, its restriction to a Schubert variety. So then the geometric connection is made by Kato-Naito-Sagaki. They formulate a Borel-Weil-Bott type theorem in the semi-infinite setup. So they basically identify the ith cohomology of the Schubert variety with coefficients in the corresponding line bundle on it. They identify it with this opposite Damasur module. If I equals 0 and lambda is and lambda is a dominant weight, and otherwise this graded character is 0. So this is the main geometric connection, and so this allows us to write Chevalley formulas. First of all, in the equivariant K-theory of the semi-infinite flag manifold. So such a formula expresses the tensor product of an arbitrary Schubert class with the class of line bundle in this T cross C star equivariant K-theory of the semi-infinite flag manifold. So what the way things went here is that first Kato-Naito-Sagaki and Naito or Sagaki gave Chevalley formulas for dominant weights and anti-dominant weights respectively. and they formulated these they expressed these formulas in terms of so-called quantum Lakshmi-Seshadri paths, so these piecewise linear paths. And then with myself, with Naito-Sagaki, we generalized these formulas to arbitrary lambda, and we found it easier to express them in terms of the quantum alcove model, which I explained, and it's technically a discrete version of these piecewise linear paths. So it's completely discrete model, which allows you to do more combinatorics with it than working with these piecewise linear paths. So let me write down the Chevalley formula now in terms of the quantum alcove models. So in the equivariant K theory of the semi-infinite flag manifold, as I said, you can formulate it. We gave it for an arbitrary weight, which you express in terms of the basis of fundamental weights with some coefficients lambda I, integers. Then you consider an arbitrary lambda chain for this weight lambda. And then we have to introduce some extra objects here, some tuples of partitions. So the tuple has partitions indexed by the set I corresponding to the simple roots. So for each simple root, you have a partition chi I. And its length is at most the maximum of lambda I and 0. So when lambda I is negative here, basically there is no partition. So you only consider partitions for the positive coefficients in this expansion. And then there are some statistics, chi of the tuple with the bars. You just sum the lengths of all the partitions in the tuple, and I of chi just sums the simple core roots alpha I check with coefficient being the first part of the ith partition, the largest part of the ith partition. So now finally, with all these statistics, I can write down the Chevalley formula. So you take an arbitrary element of the positive part of the affine Wald group, written as W translation of psi by psi. So then in this T cross C star equivariant K theory of the semi-infinite flag manifold, we have this. We have the product of an arbitrary Schubert class with the class of line bundle corresponding to lambda. It's easier to just apply a negative W0 to this lambda, but lambda is arbitrary. So when you expand this in the basis of Schubert classes, you get this double sum of various Schubert classes with various coefficients. So in the coefficients, you see these formal exponentials corresponding to the T action, and these Q variables corresponding to the C star action. So now the double sum is over objects of the quantum alcove model. So that's a finite sum. But then you also have an infinite sum over these tuples of partitions. So most of the time, this second sum, this interior sum, is infinite. But when all of these coefficients are negative here, so when the weight is anti-dominant, then I said that there is no partition for any of these i's. So then the second sum is simply missing. So you get a finite expansion only when lambda is anti-dominant. Otherwise, you have this interior sum, which is infinite, because these partitions can have parts as long as you want. And then you see these statistics that I introduced here on the quantum alcove model. N of A counts the number of negative roots in an admissible subset. You have the height of the pair WA. W is the finite Wald group part of the affine Wald group element X. And then you have this chi with the bars, and you have the weight of the pair WA, you have the end of the pair WA, the last element in the chain of Wald group elements. You have the down statistic, and you have the I of the tuple of partitions. So all of these statistics come together to give you this this very explicit form in terms of the quantum alcove model. So I also want to say that there is a representation theoretic analog of this formula, which looks very similar, but I won't write it down. I will just say that it expresses the graded character of an opposite level 0 de Mazur module for the extremal weight lambda plus mu in terms of the graded character of the opposite de Mazur module for mu. And finally, let me talk about equivariant quantum K-theory of the finite type flag manifold. So as I said, this is a quantum version of usual K-theory defined by Van Pin Lee. So here the base ring has variables Q1, QR called the Novikov variables. So you take the polynomial algebra in them, and then you take the usual group algebra of the weight lattice over this polynomial algebra. So this will be the base ring for T-equivariant quantum K-theory of the finite type flag manifold. So as a vector space, this is simply the usual T-equivariant K-theory tensored with this coefficient ring. And then there is a complicated product structure, the quantum product. So this quantum K-theory algebra has, in the similar way, it has a Z of Q and P basis given by Schubert classes, indexed by elements of the finite Val group now, because it's the finite type flag variety. So this is, so first I'll show this breakthrough of Kato, which connects the K-theory of the semi-infinite flag manifold to the quantum K-theory of the finite type flag manifold. So on the left, we have the affine information in the flag manifold. On the right, we have the quantum information in the K-theory. So somehow the extra affine information here corresponds to the quantum information on the quantum K-theory side. So Kato's breakthrough, actually it's more than this, but a big part of it is this Z of P module isomorphism respecting products between the quantum K-theory of the finite type flag manifold and a certain subalgebra of the K-theory of the semi-infinite flag manifold. So that's why it's called quantum equals affine, because you have the quantum part and the affine part. And this generalizes a similar phenomenon for cohomology, which was first given by Peterson, and then Lam-Shimozono made it very explicit. So as I said, it's a K-theoretic version of this quantum affine phenomenon. And other people like Lamli, Mihacho Shimozono, Ikeda, Iwao, Maeno, they also did some preliminary work before Kato's breakthrough. So finally, I can write down the Chevalley formula in quantum K-theory. So here you take an element, some notation, you take an element in the positive part of the coroot lattice, so written in the basis of simple coroots with coefficients d1, dr. These are called degrees. So then you have a monomial in the q's corresponding to this psi, where you just take the variable qi to the power di and multiply. So now the Chevalley formula in quantum K-theory, I said it was conjectured a long time ago by myself and Postnikov, and now we proved with Naito-Sagaki. It says that you can formulate it for the negative omega k fundamental weight. So you fix a k, a simple root or a simple weight or a fundamental weight. You take a negative omega k chain of roots. So you take a chain of roots for this anti-dominant weight. And then the formula says that in T-equivariant quantum K-theory of the finite-type flag manifold, if you take the product of an arbitrary Schubert class with the class of the line bundle corresponding to the weight negative omega k, you simply get, and expand in the basis of Schubert classes, you get a sum over elements of the quantum alcove model, all these admissible subsets, actually W admissible subsets, because you have to start at this chain of Weyl group elements at W being the one indexing the Schubert class in the left-hand side. So you get this sum of Schubert classes indexed by end of W and A. And again, you see these statistics here, the Q variables from quantum K theory is raised to the power down of WA. This down is an element of the positive part of the root lattice. So you use this notation that I explained above. And then you have the equivariant coefficient e to the negative weight of the pair WA. So this formula is now easy to obtain because we simply translate the anti-dominant Chevalley formula from the K-theory of the semi-infinite flag manifold via Kato's isomorphism. We just translate it to quantum K-theory and we get this formula. And then we have a very similar formula for the multiplication of an arbitrary Schubert class with a Schubert class indexed by a simple reflection, because that's related to this line bundle for a negative fundamental weight. So I'll end with some additional results. We have several additional results. So with Kouno and Naito-Sagaki, we also looked at quantum K theory of partial flag manifolds. So this is usually the opposite way of going. Usually formulas for partial flag manifolds are easier to obtain, and then you go to the full flag manifold. Now it was easier to obtain the formula for the full flag manifold G mod B, because that's uniform, and it turns out that the formulas for G mod P, they have to be, you cannot write a uniform formula. And we could only do it for certain partial flag manifolds. But we used the formula from flag manifolds, and we pushed it through to G mod P, again using the result of Kato, and then lots of terms cancel, and we have to use some sign reversing evolution to cancel all the pairs that can be canceled in order to end up with a cancellation-free Chevalley formula. Okay, and then another result with Kouno is related to the fact that this quantum alcove model for the Chevalley formula is actually independent of a lambda chain. So all the time I said, pick some lambda chain and write the formula. And it turns out you can pick any lambda chain and you get an equally good formula. But actually you can show that the model with all these statistics associated with them is independent of the initial choice of a lambda chain. So you can give bijections between objects corresponding to two different chains. And these bijections are supposed to preserve all the associated statistics. And it's interesting that when the weight lambda is dominant, these are actual bijections between the objects of the models for two different lambda chains. And the bijection involves some combinatorial game called generalized quantum Yang-Baxter move, which actually generalizes jeu de taquin for tableaus in type A. And it's interesting that when the weight lambda is arbitrary, then these are no longer bijections, but they are so-called psi-jections, a concept recently introduced in a different context. So a psi-jection is a bijection between sign sets. So the bijection has to account for certain cancellations that can appear. but eventually it breaks down into a sidejection breaks down into bijections between various substructures in the quantum alcove model. And then with the Kato-Naito, Kato-Naito or and Sagaki, and then with Naito or and Sagaki, we also looked at an inverse Chevalley formula for the equivariant K theory of the semi-infinite flat manifold. So if you write the Chevalley formula and you interpret the left-hand side and the right-hand side as two different bases for the equivariant K theory, then you can view the Chevalley formula as a transition matrix between those two bases. And then you can ask about the inverse matrix. So that's an inverse Chevalley formula. And for finite type flag manifolds, the Chevalley formula and the inverse Chevalley formula are given by the same coefficients. But for semi-infinite flag manifolds, the inverse Chevalley formula is more complicated. And you can write it down in terms of the quantum alcove model, but you need extra structure added to it. So it's more complicated. So I'll stop here.
Thank you. Thank you, Cristian.
Thank you very much.
Any questions for Cristian? Bob has a question. I think Bob, oh no, sorry, I saw.
Maybe I stop sharing.
Let's thank Cristian again.
Okay, thank you so much. Thank you. So I'll be, as I said, I'll be meeting Gautam next week on Friday. If any of you are there, I'll be happy to meet you and chat more with you next Friday. I said I'm coming shortly after afternoon, right? I said around 1 o'clock, I think.
Yeah, around 1 is good.
Mm-hmm. So if any of you are there, I'll be happy to meet you. If not, I'll see you in person on another time when